Okay, should be recording now. Okay, welcome everyone. This is lecture 5. We're going to be talking about cryptography and attacking crypto. This is probably going to be the most theoretical lecture you'll get from us this quarter. I am very excited about this. I am a huge cryptography fan. So hopefully you'll share in my enthusiasm today. I doubt that, but there is a homework question on cryptography, so you should probably pay attention and not fall asleep. All right, so what's the agenda for today? We will talk about mainly DES, the data encryption standard, and Diffie-Hellman, and we'll use that as a basis for talking about some of these more theoretical cryptography understandings and the principles behind them. I will try to bring some of these algorithms into how we can attack things in both a theoretical sense, so what are the weaknesses from the algorithms inherently, as well as practically how can we execute attacks against them. And they're two different things, actually. So DES and AES are what we call symmetric algorithms, Diffie-Hellman and RSA. That's the Rivest-Shamir-Edelman algorithm, are asymmetric algorithms. And so the first thing we should talk about is, what are symmetric algorithms? Symmetric algorithms are what you would classically think of when we talk about putting a lock on something. So like if we lock the door, you use the same key to lock it and use the same key to unlock it. And that's the same thing in the digital sense. We take a certain key, we use the same key to both encrypt something, and we use the same key to decrypt something. One of the most secure symmetric algorithms there are, and every cryptography class will usually talk about this, is the concept of a one-time pad. Let me just start writing. So a one-time pad is essentially this theoretically unbreakable symmetric algorithm. And the reason is because you're just literally producing bits and bits of random data for as long as what you want to encrypt is. So if I wanted to encrypt, say, a 1 terabyte document, then I will need to produce 1 terabyte worth of completely random zeros and ones. And this is going to be a very common occurring theme in cryptography, which is randomness. Your keys have to be generated via this completely random manner. So one-time pad, the key length, which is the one-time pad, the pad itself, has to equal to, in length, to the plaintext length. That's the first requirement. The key has to be completely random. And this is not just a property with a one-time pad itself, but with all further cryptography algorithms. Everything that you generate from the key itself has to be random. Within this one-time pad, this key can never be reused. So if I, again, go back to that 1 terabyte example, that means all 1 terabyte has to be just constantly generated, which is actually a very difficult thing to do in modern day computing. So if you ever heard about the Cloudflare lab, where they generate a lot of these cryptographic keys for everyone, they actually have like a wall full of like lava lamps, and they have all these technologies to generate random numbers by pointing a camera at these randomness, because it's actually very difficult for us to generate random numbers. Your computer generates random numbers by detecting different entropies within your machine. So for example, it looks at temperature fluctuations of your CPU. It looks at your mouse movements. These are all inherently random things that occur based on your environment. And that's how it tries to extract those different metrics to generate these so-called like truly or pseudo random number generators. And of course, the key thing is you can't leak the key. The key must stay secret. That is also the case for most of the algorithms that we'll be talking about. So this is the theoretically most cryptographically secure algorithm that is in existence. Yes?
So if you keep your CPU at the same temperature and move your cursor a specific way, you'll always get the same key?
Well, it's very difficult for you to keep your CPU the exact same temperature because there's a lot of background processes that are running, right? And that's why the temperature fluctuations are very minor, and your right now, like your modern computer will have something like the TPM for Windows machines or the secure enclave for Apple machines. Those chips are designed to have very specific temperature sensors to monitor these types of power fluctuations, temperature fluctuations, and all of these environmental variables, and combine them together to calculate these actual random bits. And it's because it takes in so many different factors, and it produces a very small amount of actually random bits. You have to keep a lot of things exactly constant for that to actually work. So theoretically, no, you can't just somehow keep the CPU and keep your mouse movement the same. There are still other factors that it's looking at.
If you're interested in reading more about how it works, it's called a true random number generator or a hardware random number generator. There's like a Wikipedia page on it, so if that's worth.
Okay, so that's the one-time pad. Hopefully, I'll let you know this is an infeasible thing. We send massive amounts of data over the internet. And if every single bit of internet, like a bit of document that you send, requires a corresponding bit of key to encrypt something, the internet would never work. So this is just really a thought exercise of the perfect way of encrypting something, but this would never actually happen in real life.
Well, I mean, over the internet is impossible, but the origin of the term one-time pad is because Cold War spies, they had like pads of randomly keys, and they would send secret messages using those keys.
So I would like to extend upon that. Like this was originally from the wartime, and at some point someone actually did start reusing. So remember, this key must never be reused. So someone started reusing their one-time pad because they ran out of the prefixed amount of pad that they issued. And then people were able to break the algorithm because of that. So that's why it's very important that key never reused is part of the one-time pad structure. All right, so the first algorithm that I would like to introduce to you is the data encryption standard. So this is a very interesting algorithm. It's one of my favorites. It was invented in the 1960s, 1970s by IBM and the NSA. And they originally invented this algorithm because of banks. So you had banks and you had to, like these ATM machines, and you wanted to have a centralized system where it monitored how much you took out from the ATM, how much you deposited. And all of this has to be, of course, encrypted. Otherwise, someone can modify the traffic in between, and now I have extra $1,000 in the bank. Can't happen. So IBM and the NSA decided let's make this new encryption standard. And the reason why I find this so fascinating is because most modern cryptography and what we know about cryptography nowadays actually comes from the data encryption standard, because the NSA actually has been investigating and looking into cryptography for a very, very long time. And this is the first time that they've actually produced something where it can be seen and looked at by the public. And so really modern cryptography comes all the way back from the data encryption standard of how the NSA thought process looks like, what they knew. And a lot of cryptography comes from over here. So how does the standard actually work? So the encryption standard essentially comes down to everything that's over here, this diagram over here. It's known as a Feistel network. This Feistel network takes in plain text, which is 64 bits, splits them in half into a left branch and a right branch, both 32 bits. And the right branch would go through this f function. This is the f function over here. And the left branch and the output of the right branch from the f function gets XORed together. An XOR function is, very simply put, you have two bits, bit 0 and bit 1. So your combination is 0, 0, 0, 1, 1, 0, and 1, 1. And the output is going to be 0, 1, 1, and 0. This is also the same thing as a modular 2 addition. So 0, 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2, but mod 2 is also 0. So this is also known as a mod 2 addition. And so what you'll realize is actually And then the output over here, so this branch over here from the right side gets piped down to now become the left branch, and the left branch now crosses over to become the right branch, goes through this f function again. One of the things that you should realize from this inherently is only one branch actually gets encrypted per round of this Feistel network. And that's because only this left branch at the end, this is the first round over here, actually got encrypted, right? The left branch got XORed with whatever the right branch passed into this f function is, comes out to this right branch. This right branch originally just directly gets piped down to this left branch. So what happens is, although there were actually 16 rounds going through this data encryption standard, every 2 rounds does it actually fully encrypt both halves of the message. Another thing that we should take a look at is this f function. This f function is very interesting. So it takes this half block over there, and it takes the subkey. So you have a key. The key length is actually theoretically 64 bits. But people realize that it's actually not 64 bits. There are actually 8 bits of parity used inside it. For what reason, we'll get to that. But so ineffectively, there's only 56 bits of key, and that key goes through what's called key scheduler to derive a subkey, comes down to 48 bits. Those get XORed together, put into these things called S boxes, and then the permutation function, and then that's the whole f function. So it goes through this complicated procedure. We'll talk about what these S boxes do, and it goes through all these rounds. So why do I like this Feistel function so much? The interesting thing is because it's actually very efficient. It's very efficient. There isn't a lot of things going on over here. It's just a bunch of XORs inside and also these S boxes. And the other thing that's also very interesting is this entire process is exactly reversible via the exact same function. So the Feistel network allows to exactly decrypt something by putting it straight back into the same function over here. So you take the same two encrypted text up there, and you just have to reverse the key. So if the last round was whatever subkey, that goes in the very first round, and you could derive the same thing, and now you get your plain text back. And so from the bank's perspective, it's very good because you only need one set of hardware to do both encryption and decryption. So this is the benefits of using this Feistel function. All right.
There's a question.
There's a question. Yes?
Can we explain what the S boxes are?
Yes, so I'm going to talk about what these S boxes are. So they're called the substitution boxes. They literally just take random bits. So they're actually 32 bits of data, and you get split into 8 different equal sections. So I think they're 4 bits big. Well, I think they're actually 6 bits big. I can't remember, but they're just direct mappings. So all the different combinations of these bits have a direct corresponding of something it gets transformed into. So for example, if you look at the table, it's like 000, it's going to turn into like 101, for example. So there's an exact mapping. It's just a substitution box. And so the question comes down to, why do we need these S boxes? How did these S boxes come along? And what did the NSA do to this algorithm? So that's what we're going to talk about. So the first question we should talk about is, why did we need the S boxes? And that's because of this person called Claude Shannon. You may recognize this name, Claude. That is the Anthropic AI person. It was named after Claude Shannon. Claude Shannon did a lot of work. One of them is for cryptography, which is what we now know as diffusion and confusion. So that's some properties that we have about cryptography itself. The whole point of diffusion is to ensure that when there's a single bit of plain text that is changed, more than half, or around half of it, of the resulting ciphertext. Ciphertext is this encrypted document. So plain text goes into encrypted. This is also what we call ciphertext. So if one bit of the plain text changes, if you have good diffusion, it should result in around half of the bits in the ciphertext being changed. Confusion is when your key length one of your bits of the key is changed, the ciphertext should also result in around half the bits changed. So one of the things that you should look about the one-time pad is there is no diffusion, because if there's a single bit of plain text that's changed, only one bit is going to be changed as the resulting ciphertext, because you have a one-to-one mapping of key and plain text. So these are like general guidelines as to how people now design cryptographic algorithms. And the S boxes help with this concept of confusion. Confusion being that you want one particular bit that's coming into the algorithm to be massively changed over a lot of the ciphertext. And because a lot of the algorithm that you look at in this data encryption standard is linear. Linear as in they're just a bunch of like XOR functions guided together. You can write this as a one linear mathematical function. The S boxes change that because you've inserted some completely random data inside it by doing this completely different mapping. There's no like good mathematical function to represent this. So that's why we have these S boxes in the DES. And we'll talk more. We'll come back to these S boxes a lot later on. So the question is now, how did these S boxes come about? So when this data encryption standard got published, right, it has the influence of the NSA. And no one trusts the NSA, not back then, definitely not now. So people naturally wondered, well, NSA, how'd you come up with these S boxes? And the NSA basically said, it's top secret. They're secure, trust us. And so for a long time, people didn't really believe that. They're like, well, probably the NSA, hid something in these S boxes and, made it, cryptographically like insecure. And it turns out it's not true. How the NSA did make it insecure was through the key length. So as we've said, this only takes 56 bits of keys. So that means if you wanted to brute force DES, it only takes 2 to the 56 combinations to fully brute force the entire key space. And back then, like in the 1960s, 1970s, it's impossible for 2 to the 56 to be broken. But in a couple of years' time, like the thought was the NSA would have supercomputers, capable enough to actually break this. And so even though the IBM team wanted to make the key length, 128 or even 256 bits, the NSA was like, no, we'll make it 56 bits because it is easier for us to break. And it turns out that's the only weakness, really, with the data encryption standard, is this very small key length. And later on, actually, Shamir from RSA found some potential attacks with the DES. And we will talk about this thing called differential cryptanalysis. Cryptanalysis. Okay. So what's differential cryptanalysis? Differential cryptanalysis is using a chosen plain text attack against these cryptographic standards. It's the use of lots of probability. So you will essentially have to take a large number of known plain text and known ciphertext combinations that ran through the algorithm with the same key. And from that, you'll be able to derive some probabilistic understanding of what the key looks like, and therefore reduce the amount of keys that you have to try in order to break something like DES. And it turns out the S boxes were surprisingly resilient to this attack. And this was actually in the 1990s when Shamir figured out that, it might be Rivest, I can't remember, figured out that differential cryptanalysis was a thing. And the NSA actually knew about this attack. Internally, they called it the T attack. So the NSA actually knew about this whole differential cryptanalysis thing way back when they were designing the DES. And so they specifically chose numbers for the S box that would be resilient against this differential cryptanalysis. But again, this requires a lot of chosen plain text and ciphertext combinations. So a lot of these attacks are purely theoretical. It's very hard for you to actually execute something like this in real life, especially with these resilient, like designed against these resilient attacks. The other attack that we'll briefly talk about is this thing known as linear cryptanalysis. And this is by using a known plaintext and ciphertext combination, you're able to reduce the key space to shrink down the number of guesses that you can make. And the difference between chosen and known is that known is actually a lot easier to achieve. Right? Chosen means I need to have access to this, sort of like oracle or black box of cryptography machine. I can just pipe in any number of plain text and look at the ciphertext and do a comparison. Whereas known plain text and ciphertext combinations are a lot easier. And that's because a lot of the documents that we send aren't truly random. So for example, if every single time I send a PDF across the internet and across the wire, it has these specific file bytes, or what we call magic bytes, in the file header. And that's why if you run the file command on the Linux, it's able to tell you what type of file it is. So there's these header information for every single document. That's the same. So when you look at analyze like traffic across the internet and it's being encrypted by the same key, it will likely have a very similar structure at the very beginning. So you will be able to have these known plain text and ciphertext pairs. So doing a linear cryptanalysis is actually much more feasible. And this wasn't actually known when the NSA produced DES. And so we actually know that DES is, to a certain extent, vulnerable to a linear cryptanalysis attack compared to this differential cryptanalysis attack. And so the question is, we obviously know DES is not something that we can be trusted, right? It can't be trusted. 20 years ago, when the NSA could have supercomputers to crack this with 2 to 56 key lengths. So the question was, well, how do we solve this problem, right? And of course, the answer was going to be, well, let's make a new cryptographic standard known as AES. But before we did that, what the US government did was they were like, we'll need to replace this, DES standard. But between replacing DES and using AES, there were still, a lot of banks that were running DES and were like, well, how do you protect against, attacks? Any suggestions? Well, first of all, any questions about where we're up to in this point? Yes?
Can you briefly go over S boxes one more time?
Yeah. So S boxes are literally a substitution box where you take there is literally a lookup table. You can think of it as a lookup table. So for every 3 bits, there will be a corresponding 3 bits that you just literally replace it with. And I wish I could tell you how these S boxes were made, but they're not known. But we'll talk about the AES later. And they do have a formula for deriving these S boxes. If you look into this book, there's a page where there's literally a lookup table over here. So if you are interested,
I think it's on Wikipedia too.
it's also on Wikipedia too. But there are these tables that look like this that literally tell you for every bits and bytes of these data, there's a corresponding different byte that you just replace it with. So that's basically what those S boxes are doing.
Also, an announcement.
All right, so now the question comes down to what do we do about DES, right? DES, only 56 bits of key length. Well, how can we solve this problem? Yes?
Make it longer.
Make it longer, but how do you make it longer?
Longer key.
Longer key. Well, the key, the hardware structure that's baked into the ATM machines are already there. It only takes 56 bits. So you're on the right track, right? Let's make it longer. So the idea is, well, instead of using 1 key, let's use 2 different keys, right? 2 different 56-bit keys that will equal to 112 bits, right? Great idea. That's not right. If you pass 2 DES blocks together, so as we show over here, we have some plain text input over here, and out comes some ciphertext, and there's a 56-bit key over here, and a different 56-bit key. You add them together, they equal 57 bits of security. And you're like, why is that 57 bits? And that's because there's this thing known as a meet in the middle attack. So some of you may be familiar with a man in the middle attack. This one is a meat in the middle attack. How does that work? The idea is I can take plain text, go through this DES algorithm, like I'm actually doing a brute force, which requires 56 different, 2 to the 56 different combinations, and I'll save all this output over here. So I'll have a literal list of 2 to the 56 entries over here. Then I know what the ciphertext on the other side is. I will do the exact same reverse process over here. So I'll take this ciphertext, I'll do 2 to the 56 different operations on the other end, and then I'll do a comparison. So I'll literally match whatever I get from those ciphertexts and what I get from the plain text. There should be one matching record, and those must be the 2 different keys. And so what it means is I don't actually have to do 2 to the 56 multiplied by 2 to the 56 different combinations, but I can just do this attack, and so therefore it's 2 to the 56 plus 2 to the 56, which is 2 to the 57. So this is actually a 57-bit cryptographic attack. Yes?
This would assume that an attacker would be able to get the ciphertext or the halfway. In what cases would that be true? Like, I imagine a bank would produce like a plain text and then encrypt through the whole first step or the first DES and then the second DES and then
Right.
the ciphertext.
So this requires, as you pointed out, that the attacker needs to know what the plain text and the ciphertext corresponding thing is. But what happens if you know that, right? We've shown that these encrypted documents are not completely random. We know what the format looks like. If the bank keeps sending PDF documents to you, like you go check your online bank statement, you know exactly what the format is going to look like, right? HTML websites have this doc type HTML header over there. You know what the website looks like, right? It doesn't matter if you're accessing the website or I'm accessing the website. It's going to look the same. So therefore, I know what key you're going to use. I have a chosen plain text. I know what the plain text is. I know what the ciphertext looks like. So all I have to do is just reverse that. Yes, you don't know what the actual thing in between is, but you just have to save all the 256 guesses onto one giant 2 to the 56 sheet, and you do the same thing reverse on the ciphertext end. So now you have 2 to the 56 documents, and you just compare what the different, what we call ciphertext 1 from the plaintext 1 over here, and the plaintext 1, plaintext 2 for the ciphertext 2 over here. You just do this comparison to see what's matching. So the only cost over here is actually I need to be able to run 2 different 2 to the 56 bit brute force guesses, as well as having a long enough page table to store 2 to the 56 bits of key, which if you're the NSA, you totally have the resources to do that.
Actually, a really funny application of meat in the middle of text. If anyone has heard of Minecraft seed cracking, where they take like, oh, I'm a speedrunner, I want to find Minecraft where like perfect spawn is. Turns out Minecraft seeds aren't perfectly, it's literally just a input string into a random generator, and you can use the Minecraft seed to figure out what the spawn is. So they split the seed into 2 parts and then run a meat in the middle attack to try and find the best speed running seeds. Really nice YouTube video on it. Pretty fun.
Okay, so the solution, therefore, is instead of doing a 2 DS in sequential order, we'll just add a third one over here, another DS, before we pipe it out over here. It turns out this actually works. So this one actually is 57 bits plus 56 bits of security. So this is actually 113 bits of security. So 2 to the 113. And that's because you can't do like 3 different meet in the middle attacks because you only have as you pointed out, no one actually has anything in the middle, right? This information over here isn't public because it's just within the bank system. So all you'll ever have is that P at the very beginning and that C at the very end. You can choose to do a meet in the middle attack via this way, right, to this section over here, but then you'll have to climb over 2 to the 56 bits times 2 to the 56 bits, which is 2 to the 112 bits that way, or you do it the other way, right? You come to this middle over here, and you go through this only once. So either way, you have to go through 112 bits of actual security. And so that's actually how we solved the DES problem, and that algorithm is known as triple DES. And this was actually used up until the 2010s by like still European passport agencies. They were using triple DES. Yes?
So they have like 3 keys?
So yes, you need 3 keys. But again, you can do this meet in the middle attack with the effective. So you do need 3 different 56-bit keys, but the effective key length is only 2 to the 113. So there's the misconception as to like how long a key actually is and how long is it actually effective for. So for example, the DES, the key that you actually put in to the machine is 64 bits, but it only extracts 56 bits of that key from the 64 bits because it decides every 7 bits there's an extra bit for parity reasons. That was completely not necessary. So the effective key length for a 64-bit key for DES is 56 bits. And for triple DES, even though you actually need, well, technically you need 64 times 3, so that's 192 bits of key, but your effective key length is only 113 bits. So that's what we'll be talking about for the rest, of the lecture, what the effective key length is. Any questions? Yes?
Why is there 8 parity bits in a 56-bit key?
That's because the NSA got a hand in designing this, and they want to do like, ooh, let's make it 64 bits, but we want to reduce it a little bit so we can, crack it easier. So what we actually know about the DES algorithm is the NSA used, their most advanced cryptographic measures in actually securing DES. And if you read future literature in the cryptography world, the NSA actually regretted their decision to make this extremely secure algorithm because they literally put all their secrets about everything they know about cryptography out in the world. And so from that point onwards, when everyone's studying cryptography, we're literally on the same page as what the NSA has done. So right now, like, presumably, the NSA isn't that much better than the rest of us in academia about what they know and what we know about how to break cryptography. So that's the reason. All right, so this was a standard used for a while, but obviously, as we mentioned, it's not attainable. So we have to switch over to a new cryptographic system, and I'll briefly talk about this, which is the AES. Actually, before we do that, let's quickly talk about ways of attacking, this cryptography, which is the inherent structure in key length. So key length, we've already mentioned, if you reduce the key space enough, you can actually run brute force attacks, 2 to the 56 bits of key length. I have some statistics for you. In 1999, some people built hardware-specific hardware for breaking DES, and it took them 22 hours and 15 minutes to break the DES encryption standard. In 2016, using commercially available hardware, so I just bought NVIDIA GPU off the market, it takes less than 2 days to break 2 to the 56 bits of key. So brute force attacks are real. They can break cryptography. And there's another way of breaking cryptography, which is the inherent structure, right? Their structure itself might have some inherent problems, inherent flaws with it that will lead to the algorithm being able to be broken. And these are what we call theoretical attacks, right? They break in theory. How about in practicality? In practicality, there's actually a third category of things, which are known as side channel attacks. And the majority of the non-crypto industry, crypto being cryptographic industry, are focused on preventing side channel attacks. So it doesn't matter how good your algorithm is, it could be theoretically unbreakable, like a one-time pad. They are still subject to side channel attacks, which are how the algorithm is actually implemented. One of the ways in the popular side channel attacks is something like a timing attack, where if I'm able to influence, how I generate these random key bits, then I might be able to derive information from them. If the algorithm, takes less time to run for a particular, round versus, a different round of the. Can you take a look at that? As compared to a different round of the. Okay.
You're welcome.
Compared to a different, right? So the DES, for example, there are 16 rounds of of this Feistel f function that gets run. If these f functions all take different time, and we know a smaller time means the key is actually shorter or smaller, then I might be able to derive information from that. So these are examples of side channel attacks. And before we actually had these dedicated chips in our computers that ran cryptographic functions, older machines will run them on your CPU. And so these timing attacks and other side channel attacks, by looking at your temperature fluctuations of your CPU, you can actually derive what the key could be. And so these are what practical attacks look like in terms of cryptography. Your algorithm could be completely secure, but because of the way it's implemented, it's not.
So anyone had Butner 450? Anyone remember? It wasn't like the division, but it had to do it in 32, do the operation 32 times, no more, no less. Remember that sound familiar, Simon? This is why.
So a lot of your now modern cryptographic algorithms and the way they're implemented in your secure enclave or TPM, they are exactly equivalent. So it doesn't matter if your function takes less, computational cycles to run. The time it takes to return a result is always going to be constant to prevent this type of attacks. There's also additional security measures, like they'll actually inject some completely random data into the calculation and then remove it at the end. So you can think of it as multiplying by some random number and then dividing it out at the end, but much more complicated, just to confuse any attackers that might be looking at what's going on in these chips to prevent that from happening. And of course, there are other attacks that I'm not going to talk about, but things like some people just randomly shutting down the machine just to see what kind of key is being used inside your machine and trying to derive information about that is also a potential avenue. So when your computer is completely shut down, any computations that's running on your TPM or a secure enclave just gets automatically aborted to prevent this type of attack. We'll talk more about attacking crypto later, but we don't actually have a lot of time. So let me quickly go through AES and we'll talk about asymmetric algorithms. So AES is the modern standard for cryptography. We are actually using AES every single day when we're communicating across the internet. The idea is exactly that. You have a block of 64 bits. It gets split into a 4-bit section of 16 different blocks. You first substitute bytes, shift rows, mix columns, and add round key. This byte substitution is exactly the same thing as the S boxes in DES. You shift row and you do this mixed column to introduce diffusion into the algorithm. So you make sure that the key actually gets all the way mixed into all the applications. So this is a per round thing. And you do this 10, 12, or 14 rounds. 10 rounds will net you 120, you use 10 rounds for 128-bit key, 12 rounds for 192-bit key, and 14 for 256-bit key. And there's extensive literature. This whole book is about the AES. This algorithm is also known as Rheindal, and that's because it was actually a competition put out by the National Institute of Standards and Technology to find the best algorithm to replace DES. So this was a complete open competition, and they won and became the AES. There were a couple considerations. So for example, DES was very hardware focused. That's why it's the same, you can use the same specific set of hardware for both encryption and decryption. This is no longer possible in AES. You can't just go through the same structure. You actually have to reverse. So you have to remove the round key first, reverse this mixed column, reverse the shifting row, then do this S box substitution again in the reverse way before you're able to do this, rounds to decrypt this. So that's the advanced encryption standard. I'm not going to dwell on this too much. A lot of these ideas came from DES, so things like the linear cryptanalysis, differential cryptanalysis is inherently baked into this to prevent those sort of attacks. Yes?
So DES is like more hardware-based, this is more software-based?
So they took a balance. There are very effective hardware nowadays to run AES algorithms just because everyone needs AES. But the point was software had increased, hardware has increased in capability that you would be able to just run this in relatively low-cost hardware. So the design choices was balancing how hard was it to implement this in C code and how hard is it to actually write dedicated hardware to run this algorithm. Yes?
How is this reversed to go from ciphertext to plaintext?
So the AES algorithm, you literally reverse this back up. So because this is ciphertext down here and plaintext up here, and you just do this 10 to 14 rounds, you literally get the key and you do the round key, which is just an XOR function over here. So you, two XORs you should realize actually net you the same thing. So I have A XOR, that's not the XOR sign. So if I have A XOR some key and I XOR the key again, that will actually yield you A. That's the same for modular arithmetic because those two have to be either 0 or they both have to be 1, which if you add them together in mod 2n, they add to 0. So therefore, if you XOR them back together, they will result in the reverse. Then you do this mixed column. Mixed column just literally takes the different columns and you reverse the mixing because the mixing is defined. So you just literally reverse that. Shift row is also the same. Shift row looks like, so if you have, that's what shift row does. So you have these 4 different blocks. And then you literally you shift them to the right, I believe, 1 block, and this block goes to over here. And then the third row, you shift them by 2 blocks. The last row, you shift them by 3 blocks. So these 3 blocks over here go to the front. And so you literally reverse that shifting order. And then these S boxes, if you're actually really interested, they are defined mathematically instead of chosen by random in DES by the Galois field of 2 to the 8th. If this doesn't make sense, don't worry. But they're derived from this Galois field of 2 to the 8th. And so there is a mathematical function that goes from what you're putting into this S box to what you're getting out of the S box. You're reversing this Galois field operation to get from the result to the original plain text.
So if shift row and mixed column are like defined previously, then if someone has the key, they can like put any plain text and get any ciphertext.
Yes, so that's the important thing. So these algorithms are public. So the key thing that you have to keep a secret is the key, right? You know how the lock works for the particular door. You know how it functions. So the only thing that's preventing you from getting in is by having the right key. And so keeping the key secret is why it's so crucial in the security world. Because if you have the key, you can unlock these secrets. The secret only resides in the key, not through obscuring the algorithm itself. Any questions? Yes?
So how did like the numbers of like layers like correspond to like the number of bits?
Okay, so it has to do with how this add round key function looks like. You separate these 128 bits or 256 bits of keys into this thing called key scheduler. And there's a whole, I think half of this book talks about how the key scheduler works and how you actually partition these keys to do maximum effect on this. If you're interested, you should take a read about these books. There's Wikipedia articles that talk about key scheduler. There's also key scheduler in DES as well, so this is not a new thing. All right, so now that we've finished talking about AES, we can talk about asymmetric algorithms. As you pointed out, you need the key in order to transmit data over the internet. And we can't leak the key, otherwise it renders the whole operation useless. So then the question comes down to, it makes sense for the banks because the banks come, you can go to your headquarters and you actually put the key into the machine and you bring these ATM machines to different locations across the nation. But that doesn't happen, on the internet. You can't just bake keys into machines because then every single party that needs to communicate with you has to have a different key, and it makes transmitting keys over the internet difficult, right? If I have a way of transmitting a key securely to you, then I don't even need to use encryption. I just use that different channel to talk to you. So the question becomes, how do I get this key securely to some other person? And that's when asymmetric algorithms come into place. There's a way, actually, obviously, to transmit keys to different parties across the internet. And the key idea is really this public and private key, where a person, was there some comment?
Oh yeah, you said the key idea, get it?
Yes. Definitely deliberate. the key idea is to use public and private keys. The public key is public to everyone. Private key is private. And you will take the public key and disseminate it to everyone who wants to talk with you. They will somehow use your public key to encrypt the data that only the private key can unlock. So this is the knowledge that we have now. But back then, in the 1970s, we actually didn't have this idea. So we were still trying to figure out how do we actually use symmetric algorithms in the real world. And someone by the name of Merkle had an idea. How do we get a shared key to use in a symmetric algorithm? And his idea was impractical, but it started the way of thinking, how can we solve this problem? Does anyone have any idea? Like, all we're trying to do is get a shared key. Well, Merkle had an idea. His idea was, let's take a bunch of puzzles that are difficult but not impossible to reverse. So one of these things could be like a hash function. A hash function is a one-way function, but if there's a limited amount of space, so for an example, I will always take in, say, 32 bits. Actually, back then it's probably smaller, so let's just go with 16 bits of random data, pass them into this hash function, and output would come some garbage. And I will do this many, many times and label them. So these 16 bits, for example, it could be a label like 001 all the way to like 999. So I have a bunch of different puzzles, essentially, of data, put them through this hash function so they're all gibberish. I create 1,000 of these puzzles and send them over to someone else. And assuming that it takes, 1 minute to solve each of these puzzles, then on average, you would need 500 minutes to be able to break this. So we'll just make this, the number of these different puzzles that you have to solve extremely high, and maybe the amount of time that needs to solve them high, but not impossibly high. So maybe within some constraint, say you're willing to wait 5 minutes to exchange a key, then it'll be 5 minutes. And the idea was you, the receiving party of all of these random puzzles, would just pick one of them at random, go through this process of getting from this gibberish back to this original plain text, of which you'll have a shared key. Now, obviously, you should see a problem, which is it requires a huge amount of time to, first of all, solve these puzzles. If the smaller the puzzle it is for you to crack it, the more amount of puzzles you'll have to generate in order to maximize security. So what you do is let's say I generate 4 billion of these different puzzles to send them over. If they're at 1 minute to solve each, then you require 4 billion minutes, or actually on average 2 billion minutes to solve and find the right key that's used in the conversation. So that was Merkle's original idea. Obviously infeasible, because it requires both a lot of time to solve and also a huge amount of data that's transmitted that's basically useless because you're only choosing one of these puzzles to solve and everything else is junk. So that's the first idea of how we get a shared key. Then two people from Stanford, Whitfield and Martin Hellman, came up with a better algorithm to solve this. And this is the Diffie-Hellman algorithm. And I will try to go through this in full because I think it's a very simple algorithm, and I think everyone should know about this. And the idea is we will have some public information. So we will go with the default Alice and Bob, who want to talk with each other. And we have someone who's listening in the middle called Eve. So what Alice, Bob, and Eve will know ahead of time is some number G and some large prime number P. Alice would generate a number 8, which is just number from 2 all the way to P minus 1. So this is a random number that Alice keeps secret. She will take G, which is a public number, raise it to her private number A, modulo P, and we'll call this number big A, and send this across the wire. So now Eve knows this big A number. Bob will do the same. He will call his private number B, also a number from 2 to the P minus 1, and Bob will raise this to G to the B, modulo P, and we'll call this big number B. Send this across the wire, B. So how does this help? Well, it turns out we'll take B, raise this to the private number that Alice got, which is A, which, if you remember, capital B is just g to the power of B raised to the power of A. So that yields g to the power of A, B. Bob will do the same. Take capital A, raise it to the lowercase letter b. That equals to g to the power of A to the power of B, which is just g to the power of AB. What does Eve know? Eve knows GP, and remember, all of this is modulo P, by the way. Eve knows GP, A, which is just g to the power of A mod P, and B, which is g to the power of B mod P. So the maximum that Eve could know is something like g to the power of A times g to the power of B, which is actually equal to g to the power of A plus B, which is not g to the power of AB. So this would be what the shared key is, and Eve would have no way of knowing what the original secret is, even with those information. So the idea of this, the security of this algorithm is known as discrete logarithm. So this is the discrete log problem that says if I know some value y equals to ax mod p, p being some prime number, and if I know the values y, a, and p, and a is a generator of p, so generator meaning primitive root in mathematical terms, there's no way of reversing this to x. And this is an unsolved mathematical problem. Name of it is, again, discrete logarithm. And as far as we know, this is not breakable. And so the Diffie-Hellman problem actually introduces a couple extra things that you do know about, like you do know these extra A and B values. So if we come back over here, we not only know this GP value, but we also get this extra information. So this extra information might actually help you solve the Diffie-Hellman problem, but as far as we're understanding, that doesn't help either. So that's how we get a shared key from Diffie-Hellman without going through these thousands and thousands of Merkle's puzzle boxes. Any questions about Diffie-Hellman? I can see yes.
Are A and B necessarily prime or co-prime to P?
No. So only P needs to be a prime number. A and B are just random numbers that they derive themselves, and they don't share with anyone. Yes? What's the point of P being prime? It comes down to this discrete logarithm problem. The reason is because we want this A value, or in this case, what we're calling the G value, to be a primitive root of the prime number P. And that means we want to be able to facilitate the function of if I'm able to do something like G to the power of 2 all the way to P minus 1, those should all spit out different values. And a lot of numbers don't have generators, especially if you're a non-prime number. And so that means you're reducing the amount of possible keys it is for this to work. So because of the fact that G to the power all the way from 2 to the P minus 1 all produce distinct different numbers between 1 and P minus 1, therefore we know that there are exactly P minus 1 possible keys for us to use. And so that's why we use these large prime numbers. Any other questions about Diffie-Hellman? Okay, so how does this relate to our previous structure over here, which is public key and private key? I will tell you Diffie-Hellman has a public key, and they also have a private key. Who wants to tell me what they are? Let's come back to this algorithm over here. What's the public key? What's the private key? Yes?
The public key, like what Eve knows, like the G and P, and then like the private key is like what Alice and Bob know.
Yes, so the private key is the small letter A because only Alice knows that. Bob can't know this information. And the public key would be this G, B, GP, and this capital letter A. So that would be Alice's public key. So if someone wants to talk to Alice, they obviously need to know big A, the G, and the P, but they will never know the small letter A. So this is the private key. and then the combination of G, P, and G to the power of A will be Alice's public key. And then correspondingly, of course, Bob's public key is just small letter b, and the public key is G, P, and capital letter B, which is just G to the power of B modulo P. So Diffie-Hellman were pretty happy with this. They named they wrote up their results in a 1976 paper called New Directions in Cryptography, and they began their paper with like, this is a new era of cryptography. We've solved this big problem. But there was one problem that they weren't happy with about Diffie-Hellman, which is they didn't actually solve, well, they solved the encryption problem, but there was another problem that they wanted to solve with cryptography, which was verifying that in the CIA triad, the integrity part of it. So if I sent, the CIA triad, which is the confidentiality, integrity, and availability, the I part, so this solved the confidentiality problem. Right now I can exchange the key with you, and now I can send you, messages that are encrypted via, a symmetric algorithm. But I didn't solve the problem where I wanted to prove to you that this message came from me. So if all of you knew my public key, and I had my private key, with this algorithm, what we're seeing over here, there isn't actually a way for us to prove to all of you that a message that came from me actually came from me, right? It could be subject to forgery. So we wanted this thing called a digital signature. And Diffie-Hellman couldn't solve this problem. But less than 6 months later, RSA, Revesh, Shamir, and Edelman came up with a slightly better algorithm, and I think more famous asymmetric algorithm that did solve this problem. And they didn't use discrete log. They used the difficulty of prime factorization. And this is how it works. How much time do I have? Okay, I have time. So how this works, and this isn't strictly necessary knowledge. I'll just include this because I think it's fun. And so if you don't understand what's going on here, don't worry too much. But we're going to take an n value, and we're going to take two prime numbers, p and q. And in order to encrypt something, we're going to create some ciphertext, and that ciphertext is very easy. We're going to take p, which is this big prime number, raise it to a number e, and modulo n. And this e value has to be equal to, they have to be co-prime with the phi function of n equals 1. Phi function just means the number of values that are co-prime to n. So for a prime number, there are always p minus 1 number of co-prime values that are number of numbers less than p that are co-prime with itself, because it's a prime number, so there are no numbers that's less than itself that would be prime, relatively prime with itself. But because n is two prime numbers multiplied by each other, phi of n is actually, I believe, p minus 1 times q minus 1. So you have to make sure that the greatest common divisor is actually equal to 1 for that e value. That's not strictly important, but just telling you. So you would just take the ciphertext equals to p to the power of e modulo n, and the public key is n comma e. So that's your public key, and you can produce ciphertext like that. And for you to decrypt the text, you will just take the ciphertext. This p is, by the way, is your message, so maybe I should use m instead of plain text. So that's the message you raise to the power of e modulo n. That's your ciphertext. And your ciphertext, in order to decrypt it, you will take c to the power of d modulo n, and that's equal to your original message. E and d are equal or congruent to 1 modulo phi of n. So this is actually a very simple algorithm. If you know how to calculate these phi of n values, which is just p minus 1, q minus 1. So you're literally just taking the multiplicative inverse of your public key of e to find your private key of d. So this is the public key, this is the private key, and they are related by multiplicative inverse. And in order to find these values, you have to be able to find phi of n. In order to be able to find phi of n, you have to know how to calculate p minus 1 times q minus 1. And if P and Q are these numbers that are hidden from you because your public key is only N and E, that means the difficulty of RSA is how to factor this N back to P and Q. And the reason why this is so useful is because we can actually do digital signatures now. The digital signature actually just looks exactly like this decryption algorithm, because now I'll create this signed algorithm S by your message. Usually you take the hashed function of your message that you want to prove that comes from me. I raise it to the power of D, which is my private key, modulo N. And in order to prove that comes from me, you can verify the signature, verifying the signature by doing S mod to the raised to the power of the public key E modulo N. And because we know S is just M to the power of D raised to the power of E, that's just M to the power of DE, which, as we've said over here, is just equal to 1. So that equals to the message. So I'm able to effectively create a digital signature and an encryption scheme with this very simple algorithm. So that's RSA, reverse Shamir-Edelman. And if you didn't understand any of this,
Ethan also has office hours right after this. You can talk to him.
Yeah, you can come and ask me. I'm happy to talk more about this. Again, I like this a lot, but that's RSA. So now we've actually figured out both using an actual public-private key to communicate by encrypting and decrypting messages, as well as signing messages. I think someone called Elgamal actually came along 5-10 years later and retroactively applied this to the discrete algorithm problem. And I'll give you a very brief overview of how the discrete algorithm signature looks like. Over here, the Diffie-Hellman Elgamal signature looks like. So we've established K is equal to R to the power of A mod P. Your R, P, and K are your public keys. So in order to create a signed message, you say R to the power of K, M, K, K, M being your message, and this big K is some random value. And then you would create a signature. So that's your signature. You verify the signature by R to the power of K, raised to the power of A, multiplied by M, K to the power of K, because this is the signature that's generated. That would equal to M modulo P. So this is a very messy algorithm to do a digital signature, but this is known as the Elgamal digital signature. So what Diffie-Hellman came up with actually also does work for digital signatures. But this is also the basis for DSA, if anyone's interested in that. But like very evidently not as elegant as RSA. All right, so now let's talk about how do you break these things. This is from NIST. This was published in 2020, so actually 6 years ago, but relatively unchanged. And that says comparable security strengths of symmetric block ciphers and asymmetric key algorithms. So for an AES 128-bit key, you need 128 bits of brute force power to actually brute force all of this. If you look at RSA or you look at Diffie-Hellman, the equivalent of 128 bits is actually 3,072 bits. So that's a lot of keys in order for you to actually achieve the same security strength of AES 128. And AES 128 is like the standard now. Like that's the minimal security you need in order to break that. So these are a lot and lots of bits that are required in order to do these key exchanges. And so luckily, we actually have newer algorithms like ECDH, so elliptic curve Diffie-Hellman, so elliptic curves instead of using this like traditional G to the power of A, we have this nice curve. That's not what it looks like. It looks like that. So that's like an elliptic curve, and you find points on them and you add them together to produce that same discrete logarithm problem. So it's the same principle as Diffie-Hellman. You still use discrete logarithm, but using elliptic curves and points on this elliptic curve, you only need about double the amount of bits, so around 256 bits, to achieve an effective security length of 128 bits. And so if you look at modern browsers, you will see that you're using some form of ECDH for doing an initial key exchange, because these key exchanges are always going to be more expensive than using symmetric algorithms. Therefore, you're only using the asymmetric algorithm once to do a key exchange, and then you're always going to go back to your default symmetric key algorithm to do the rest of your computations. Any questions here? All right, so this cryptography lesson will not be complete without talking about quantum computing. So what does that mean? What would quantum computer do to our existing cryptographic standards? Well, first of all, I'm sorry to tell you that everything that we've talked about RSA and Diffie-Hellman, they're all easily breakable when we have a powerful enough quantum computer. It doesn't matter how long your key gets, they are literally breakable in like seconds. So your exponential time to create these algorithms requires constant time via an algorithm known as Shor's algorithm. So Shor's algorithm will just break all of our currently used asymmetric algorithms. That's bad news. How about symmetric algorithms? Well, better news over there. So there's an algorithm known as Grover's algorithm. And Grover's algorithm will essentially cut the effective key length in half. So a 128-bit key will essentially be around 64 bits, which, as we've said, is breakable. And a 256-bit key will become around 128 bits. And as far as we're concerned, 128 bits is usually good enough. And so when quantum comes along, we're all screwed, right? We can never do key exchanges again. And the answer is kind of yes, kind of no. These algorithms were a long time ago, again, 1976 for Diffie-Hellman, 1977 for RSA. NIST has, because of finding out that quantum might be short-term away, have been developing new algorithms known as quantum-resistant asymmetric algorithms. And they, instead of using prime factorization or discrete logarithm algorithms, they use now lattice-based algorithms that are thought of to be not crackable by quantum computers, nor crackable by classical computers. So Shor's algorithm, we know for a fact, doesn't break these lattice-based algorithms, but we don't know if there exists a different algorithm that might break them as well. So if you look at your browser nowadays and you look at the symmetric key algorithms, you'll most certainly see something like ECC25516 with a bunch of other numbers behind. And that's because it does a symmetric key algorithm via the traditional elliptic curve Diffie-Hellman, as well as the new lattice-based thought to be quantum computer resistant algorithm to do this full asymmetric key exchange. And the reason is because we also don't have enough literature to prove that these new lattice-based algorithms are also resilient to classical computer attacks. So therefore, we just use both.
There's like a whole realm of post-quantum cryptographic protocols. A lot of communication apps, like I think iMessage right now uses post-quantum cryptography for end-to-end encryption. But then there's a lot of apps that, or like a lot of applications in general that still use dated encryption protocols. Algorithms, that's what's called.
So your strategy as of right now is don't get on the target of the CIA or the NSA or insert state surveillance agency here that might get a quantum computer as soon as we get fusion technology or something.
So yeah, so we actually do know that nation states are starting to save network traffic in anticipation of being able to just decrypt them with quantum computers later on. That's why we're just starting to use, even though they're unproven, quantum algorithms in key exchanges. All right, if there's no questions, there should be a big question, which is, what's the point of this lecture, right? I know it's main part of it is because I love cryptography and I really want you all to learn something about cryptography, sharing my passion. But
And they don't teach cryptography anymore.
And they don't teach cryptography anymore, which is very sad. But what do I want you to take away from this lecture, right? Who has an idea? What do I want you to take away from this lecture? Yes.
Don't use ancient outdated cryptography that like DES.
Okay, don't use ancient cryptographic technologies like DES, okay? Yes?
Even though the math is secure, or maybe secure, the humans are the most vulnerable parts of any system.
Well, that's definitely true, right? In all security, even anything that we talk about later on, doing these defense in depth and these attacks, a lot of it does come down to humans, right? Humans in the loop. Humans are always going to be the weakest link in the chain. And whether or not whatever systems you implement, right, whatever security measures, whether it's cryptographic security measures, whether it's some other type of access control, humans are always going to be the weakest link in the security. But yes, very important. You forgot. Okay. My main takeaway is a lot of cryptographic experts will tell you, don't roll your own crypto. Which is, unless you have multiple advanced math or computer science degrees, or you work for one of those 3-letter agencies, you should never try to use your own cryptographic algorithms. The key in cryptographic algorithms is that security resides in the property of your key. If we come back all the way in one of the earlier slides, right? Ideally, when we talk about these ways of attacking crypto, we want to eliminate problems with inherent structure. So we want the entirety of the security of the algorithm to be reliant on the key length. And if you do your own cryptography, like we've shown, like just because you add 2 DS algorithms doesn't mean you effectively double in security. That's not what's happening. And so it's very important that these crypto algorithms get either vetted along by the NSA, who have experts at these things, multiple experts that look at this, or you actually publish these algorithms, have it looked out by the wider cryptographic community in order to figure out, like, are these algorithms actually secure? And so that's the main idea I want you to take away, is making your cryptographic algorithms are very difficult. And I haven't even scratched the surface, right? I only talk about symmetric and asymmetric keys and asymmetric and symmetric cryptography algorithms today. There's a lot. There's still hashing algorithms. There's things like zero-knowledge proofs that are very fascinating topics. And we've only covered 2 of those symmetric and asymmetric algorithms each. And so it's very difficult to design actually secure algorithms. And that brings me to your assignment. I didn't listen to the advice that I gave all of you, and I decided to create my own algorithm. So what that means is you get the sim.c protocol that I specifically designed. It took me a whole day to design this, so you better appreciate this. This is definitely a vulnerable protocol. It's subject to all sorts of attacks, your creativity being your only limitation here. But I lost the encryption key, unfortunately. I do require you to decrypt my message. Can't remember what that message is. So I've given you the ciphertext. I've given you the protocol. And so again, if you come back to the lecture, right, your 2 ways of attacking it is just inherent structure and key length. And there's no side channel attacks because the algorithm that I've produced isn't actually running on the computer. It's not running on the servers. It's not, you can't go and do these like timing attacks. You can't go and look at the temperature variations. None of this. So you're only left with the inherent structure and the inherent key length of the algorithm. And that's my biggest tip for you. Look at what the protocol is doing. It's not that complicated. It's only less than 100 lines of C code. You should be able to figure that out. In fact, to decrypt this solution that I quickly wrote doesn't even require more than 20 lines of additional C code that you can write to solve this problem. So that's what I have to offer you. The file is compiled on X, for those other 2 problems, they're compiled on x86 machine, but this one, it's in source code form, so you can actually run them on any machine you want. But yeah, that's what I have to offer. Hopefully you take my advice. Don't do what I do and write new cryptographic algorithms. They're not secure. And yeah, thanks for coming. Yeah, I will end the recording.